Okay, so we're talking about configuration, and as it says here in the abstract, determining relative configuration by chemical transformations was a painstaking and sometimes ambiguous task. We looked last time at the beginning of that. I'll review that just briefly. But recently there's been very substantial progress made toward calculating optical rotation, whether it should be plus or minus and how big it should be, by quantum mechanics, which sounds easy but turns out not to be so easy. So last time we looked at the first table in this book about an atlas of stereochemistry that showed how to relate glyceraldehyde, which Fisher had chosen as his reference and called capital D, to lactic acid, which, as you see, is related to a whole bunch of other compounds. You can see all the tables in which it also appears down at the bottom, A8, A12, A22, and so on. Now, notice that D, capital D, doesn't mean it rotates light to the right. Plus, or small d, means it rotates light to the right. And among these things that were related to one another by chemical transformations, there are an equal number that rotate light to the right and to the left. So obviously it's a subtle thing. So in here, this lactic acid was so important that it was related by lots of people in different ways. Here's another example. And in this particular case, I assigned you a problem for today to consider, even though we haven't talked about nucleophilic substitution reactions directly yet, to consider what HOMOs and LUMOs would be alternatives for different ways that hydrogen iodide might convert that alcohol on the left to the iodide on the right, with X being iodine. So I'm sure you've done that and you'll be primed for a discussion of it. But to really know how these things work, you at least have to look at the references that tell how the reaction was taken out. Reference 8, reference 2, reference 5 here. And if you look down at the bottom at the references, you see that some of them are pretty old. They're much older than this. Some, reference 8 that we talked about above is from 1914. But Levine at Rockefeller Institute in New York was a very important player in doing these correlations. So he's the one that did 5 that we looked at above. And you can see here he is again doing all these things that are numbered 10 in order to get to butanol, which then gets to lactic acid. Right? So, if you wanted to really find out how it happened, you could have talked to Levine, but you would have had to be here in 1931 when he spoke in this building at the 4th Organic Chemistry Symposium, and his title, as you see, was Chemical Structure and Optical Activity, the very stuff we're talking about now. And in fact, back in the rear here, this young fellow, 24 years old, is Paul D. Bartlett, who's, as you remember, your chemical grandfather, who was working at that time with Levine on this kind of problem. So we could have asked him, but unfortunately he's not around anymore. But the number 2 reference in this was another thing involving 2-butanol by K.B. Wiberg, which was published, as you see, 25 years later, after this had already been done by Levine. And this is the paper that talks about that from 1952, the stereochemical relationship between 2-butanol, that's the compound in the upper left there, and lactic acid by Kenneth B. Wiberg. Now, Wiberg at that time was just 24 years old, and he had just become a professor at the University of Washington, having progressed rather rapidly through his undergraduate and graduate work. And he was, like so many other young people, Van Hoff and so on, you can see that he wasn't afraid to challenge accepted authority. It says here, much of the available evidence, and you can see that the evidence is that paper we were just talking about, reference number 5, concerning the relative configuration of 1 and 2, is not entirely satisfactory for several reasons, the most cogent of which is the uncertainty associated with one reaction in the series employed, which is this scheme on the right. And that's the thing you were trying to do for your homework today. But Wiberg went on from this promising start to be the real leader in physical organic chemistry and understanding how organic molecules are structured and how they react. Here you see him looking through a magnifying glass at that pathological bond, which we've looked at before in a different context. Remember where the bond doesn't actually exist? And he's always been at the forefront from this work at the beginning on classical stereochemical correlations to the very latest thing, which is using quantum mechanics to try to figure out how molecules rotate light. And fortunately, you're not too late to hear him. Here he is. Just put that in your pocket somewhere. That's fine.
Well, it's a pleasure to have an opportunity to talk to you about some of the things we do, especially since I think this is one of the most innovative organic chemistry courses in the country, and you're very fortunate to have Professor McBride as your instructor. Now, he's dazzled you with these marvelous PowerPoint presentations throughout the year, but I'm more old-fashioned. I started teaching in 1950. At that time, when we gave lectures someplace, we went out, we drew things on a piece of paper, got someone to photograph it, and convert it into a lantern slide like this, something between two pieces of glass, and we brought heavy box of these to a lecture someplace. There were no computers. There was no Microsoft, no PowerPoint. Bill Gates hadn't been born yet. He was born in 1955. So I gave my lectures using a piece of chalk and blackboard, and I like to talk with a piece of chalk in my hand, so that's what I'm going to do today. Now, the topic today is optical activity, or more specifically, optical rotation. Now, how do we measure it? Well, you had something about that before, but I thought I'd show you a polarimeter cell. This is a cell in which we put the compound that we want to study. It has quartz windows on both sides, so no light will be absorbed. And we send polarized light in from one side, monochromatic polarized light, most commonly using the sodium D line, the yellow color that you get when you heat a sodium salt to high temperature. So that polarized light comes in here, and we have another polarizer out here. And when the cell is empty, we set the two polarizers so that no light comes through, put the compound in, and then you can see something if it rotates the light. And we rotate a polarizer. It has a scale on it to indicate degrees. We rotate it and we can measure the rotation. So it's a very simple experiment. You can see that it's not a very strong signal. If you look at an infrared spectrum, you usually use a cell that's between 1 millimeter and 1/10 of a millimeter in length. This one is 1 decimeter, 100 millimeters. So it's a very small effect, but it's one we can measure with high accuracy. The new modern polarimeters, you just plop this in, close the cover, push the button, and an LED display gives you the rotation angle to the nearest thousandth of a degree. Pretty easy these days. Was much harder once. Now, this whole business of optical activity, we have some kind of reference, as Professor McBride pointed out. So a common one is glyceraldehyde. And this the natural glyceraldehyde has a positive rotation, and as Professor McBride mentioned, Emil Fischer called that D. Now, he didn't know if this were the right representation. The molecule is not planar, so two of these groups have to be back and two have to be forward. He didn't make a guess. So this is his guess. Now, he could have been wrong. There's a 50-50 chance he was right. Would it make a difference? Well, until very recently, the answer is no. It made no difference at all. All the structures that are written down based on this could have been the mirror image of the real thing, but if no one had invented a method of determining absolute configuration, no one would be worried about it. It really doesn't make any difference so long as you're consistent. And that's the idea of the relative configuration. Now, the relative configuration of lactic acid is similar to this. That's an acid group on top, here an OH, and here CH3. Now, there are ways to convert aldehydes to acids. There are ways to convert a group like this to that in an indirect way. This is lactic acid. The acid that builds up in your muscles when you exercise too hard and makes your muscles ache. This has a minus sign rotation. It has the same conformation. The groups are all arranged in the same way as here. There's a different sign of rotation. That's all right. So long as we know the relative signs for compounds that have the same configuration. Now, another compound that is important and relating to lots of other compounds, as McBride mentioned, is 2-butanol. And so the question of how does one relate 2-butanol to lactic acid or glyceraldehyde, there's no question about the relationship between these two, but what about 2-butanol? As Professor McBride mentioned, Levine took up this problem, and what he did was to start out by taking acetaldehyde, treating it with base in a reaction that Professor McBride will talk about later on, and have an aldol condensation. Now, I don't want to spend a lot of time on the details of an aldol condensation. So this piece and that piece come from two different molecules. Now, this has a potential of having a chiral center here, and so what Levine did was to reduce it with yeast and some sugar. Now, the marvelous thing about yeast is that it's a natural compound, so it's chiral. All natural compounds are chiral. And in the same process that yeast converts carbohydrates to ethanol and gives us our neutral grain spirits that can be used legally in various drinks, it'll reduce this. Let me see. Did I get it wrong? Yeah. What did I do wrong here? the compound we want to get and I haven't done this for a while, so I confuse myself sometimes. So a compound with this structure, reducing that, will produce this. Now this is a compound of its importance. So we forget about the rest of this. We just look at what he wrote down for this compound. Now, this compound had been related in some of his previous papers to glyceraldehyde. So what he wanted to do is convert this OH group to a hydrogen. And he did that by adding hydrogen iodide. And he got what I think is a remarkable transformation. Now, we know from studies of alcohols that if you treat them with compounds like hydrogen iodide or hydrogen bromide, they're converted to the corresponding halides. But we know that tertiary alcohols are normally more reactive than secondary. This is a secondary alcohol, so 2 carbons attached, and that's more reactive than primary, one that only has 1 carbon attached. So, why does it react here? Well, that's very strange. So you wonder, maybe something else is going on. Well, one possibility would be and we protonate this oxygen. Oxygen is easily protonated. Water is protonated to make HCO+. Alcohols, the OH gets protonated. And now a lone pair on this oxygen can come in and displace out water. And make this 4-membered ring. This sort of thing happens frequently in organic chemistry. It's known as a neighboring group reaction. Some neighboring group comes in, does something, and then its participation is lost in the final act. Here, for example, iodide ion can come in and displace this, and we get that. So at this point you say, what's the big deal? Why go through this rigmarole to show you get that? But now the other possibility is we can rotate this group around. Rotation about this bond doesn't affect configuration. Configuration is just what groups are present. The exact arrangement is conformation, but configuration is only concerned with what groups are present. So if we rotate it around, we can get that conformation for the same configuration. There's no difference between this and this. It's the same compound. But now, if we protonated this oxygen, then this pair of electrons can come in and attack that carbon, push out water. And what will it do? Well, it'll make this hydrogen swing over to the other side. Now it has to move for this to come in. So if we do that, now what we've done is to invert the configuration of this carbon. The oxygen was originally on that side, now it's swung over to this side. It's a different oxygen, it's on this side. And now if iodine comes in and attacks here, we will not get this, but we'll get the enantiomer. It'll be the opposite configuration. So now the question is, how's the reaction go? We have three possibilities. We might just protonate this oxygen and displace by iodine, get this directly. Or we could go through this four-membered ring, intermediate, or we could go to this four-membered ring, intermediate. So we have three possible ways for the reaction to go. And if we have that, then we just don't have knowledge of the relative configurations. So how do we get around this? Well, we can do some other reaction. And the one I did in 1952, to start out with this compound. We have a double bond here. Now, if you have a carbon-carbon double bond, I'm sure you've heard, you can add hydrogen to it. In the presence of some catalyst, add across that bond, and we end up with Now, what we can also do is to protect this OH group. One of the big things in organic chemistry is protecting groups. If we have more than one functional group in a molecule and we want to carry out some transformation, we often have to do something to that group to protect it. And what we can do is add a methyl group treated with methyl iodide and some base. The base pulls off the hydrogen, makes O-, displaces on the methyl group, and so we get a methyl ether. Now that allows us to oxidize this to an acid group. It's a two-step oxidation, but I won't give you all the details. The important thing, it does not involve any of the bonds. And you see that's related to lactic acid, and in fact one can convert lactic acid to this, converting that OH in lactic acid to this. So this is directly related to lactic acid. So that's related to lactic acid, and here we have 2-butanol, and so we know the relative configurations, and it turns out that Levine's assignment was correct, which means either that this was protonated and iodine attacked it directly, or that we got this four-member ring intermediate with iodide attacked, and we don't know which way it is. We have no way of telling at this moment which way the reaction occurred. But Levine was lucky. It did not involve an inversion configuration, and so that's fine. So the point of this is simply that we have to know what's going on in a reaction if we want to get relative configurations. It's not enough to convert one compound to another. We have to know what's going on. And we have to be sure that nothing happens at the carbon of interest. Because if a reaction, anything occurs at that carbon, we can get inversion configuration or get retention configuration, and we end up not being sure of anything. So that's the lesson about this. Now, why is all this important? This work of Levine was done in 1927. My work was in 1952, and there's been some sporadic work from 1920s to the 1960s, but it wasn't a subject that was really of great interest in most chemists. No, they said, all right, that's nice to know, but what's the big deal? But then, we came to a realization that all compounds in biological systems, if they have a chiral center, we'll have one enantiomer and not another. We can't use the wrong type of amino acids. We can't use the wrong sugars. We simply can't digest them. So we have to have the right compound. And so chirality becomes important. It becomes sufficiently important recently that the two new journals within the last 20 years, one named Chirality, the other Tetrahedron Asymmetry. When a new journal appears, the subject has gotten interesting. They don't produce new journals unless they're sure they can sell them. So now, also important that we found that enantiomers of drugs often have very different properties in biological systems. One enantiomer could kill you, another could cure you. You want to make sure that you've got the right one. So this whole business of configuration has become quite important. Now, what about this question of what's correct here? What is the absolute configuration? Professor McBride will tell you next time how that's determined. But as I said, until recently, it wasn't much of a concern. And there are two reasons for being concerned at the present time. One is lawyers, and the second is computing. Now, if you take out a patent, you have to specify the structure and configuration of the compound that you're patenting. Suppose you got it wrong. Well, a lawyer from some other company would say, ooh, he goofed, and invalidate the patent, or at least try to invalidate it. So one have to be sure of the configuration in order to get a patent that's valid. At the same time, we can now calculate rotation. Now, there's only been some that's been in practice possible since about the middle 1990s. It was originally, the theory was developed in 1927 by a fellow by the name of Rosenberg. And that's just about a year after Schrödinger proposed his wave mechanics and started quantum mechanics. So optical activity was a subject that was considered very quickly after Schrödinger's theory was developed. Now, it would have been very frustrating if the work on these compounds were wrong. If Emil Fischer's guesses were wrong and everything was backwards, then you start calculating these rotations and you always come out with the wrong sign. This would be very frustrating for theoreticians. But fortunately, Fisher got it right, and so when Rosenberg developed this method, and we finally got computers that could handle the theory, the theory was fine, but couldn't handle it without some large computers. And so this languished for 70 years because we didn't have the appropriate computational tools. But now, I'll try to give you sort of a cartoon version of what's involved. Don't take me too literally. I'm just giving you sort of a guided view of what's going on. Light is propagated as an electromagnetic wave. And so we have a sinusoidal wave, not a very good sinusoid, but the spacing gives you the wavelength. And if we use polarized light and we use a single frequency, then this will be a coherent wave and it'll be all in one direction. Now that's the electric part. There's a magnetic part that goes with it. Magnetic part comes in and out of the plane of the board. It's just this turned 90 degrees. So there's an electric component and a magnetic component. Now, if we want to rotate the plane of polarized light, what we have to do is sort of grab hold of both the electric and magnetic parts and rotate the whole thing so that we rotate the plane of polarization. Now that's basically the idea of Rosenberg's theory. To tell you about it, I have to define two quantities. There's an electric transition moment, and I can illustrate that by thinking about a double bond. Double bond has a pi system. The two p orbitals are in phase so that it's attractive. But there also is a pi star orbital which is unoccupied. And we can have pi to pi transition. We take an electron from an orbital like this and transfer it to an orbital like that. Now, there's a certain energy associated with that. That energy is concerned with the wavelength. You have to have the right wavelengths in order to get light to be absorbed. But it's also a question of how strongly absorbed. Now, that's what this electric transition moment is. To get it, it's called m, and in the x direction, it's the integral of that times the coordinate times that integrated over all space. Now, what does that mean? Well, x, the coordinate, is just something that goes like so. Minus on the left side, right on plus on the right side. Now if you multiply this by this, this by this, we'll get something that looks like this. If we take a product of that and something that looks like it, integrated all over all space, we'll get a number. And that's the electric transition moment. And the larger it is, the more strongly the compound absorbs. So there's also a magnetic transition moment. And that's usually abbreviated mu in an x direction. If we have, say, a carbonyl group at one carbon, we'll have a p orbital that comes in and out of the board, which is occupied by a lone pair electron. I'm saying this is an oxygen. so carbonyl group. There's a lone pair on that oxygen, and one component is in and out of the board. And then we still have this pi star. So this is called N. And now what we want to do is do something to this to make it look like that, or vice versa. Now what we can do is use the angular momentum operator. Angular momentum operator rotates. So if we take this and we rotate it 90 degrees, it'll line up with this. And so the product of this times angular momentum operator times that, integrated over all space, is the magnetic transition moment. Now this is the simplest example. Compounds typically have orbitals that go over lots of the molecule, and there'll be some component of the magnetic and some component of the electric transition moment. So what Rosenberg said, what you have to do is take the magnetic moment times the electric moment divided by the difference in energy between the molecule and in a given excited state. You have to take the sum over all excited states. So in a typical molecule you have lots of orbitals. There's 0 and lots of orbitals up here. And these are all filled, 2 electrons in each one, so on. And these are all empty. And every excited state can be formed by taking one of these electrons, any one of these orbitals, put anything up here. So lots and lots of combinations. So this sum is over all combinations, so taking one electron out of one of these orbitals, putting it up here. Now, multiply that by a constant, and you get the rotation in the x direction. And the rotation we measure is given by the x component plus the y component plus the z component divided by 3. And that's because, all the molecules are rotating all the time. We can't stop them from rotating, so we have to take the average of the 3 components. Now there are some people, a former postdoc of Professor McBride, who's trying to measure these individual components. Very smart person at NYU, Bart Carr, and hopefully we'll end up by getting quantities like this. But at the moment, all we can do is measure the average value. And the specific rotation is given experimentally by alpha divided by the length of the cell in decimeters times the concentration. And the concentration is in grams per milliliter. And usually indicated wavelength for sodium, D, and then temperature. So we can do these calculations, and we can calculate a rotation. Now, this has come a long way over the last 20 years. So at the present time, we can calculate rotations pretty well. But there's a catch. There's always a catch when you do a theoretical calculation. It's for the gas phase. And we're not measuring rotations in the gas phase, we're measuring the solution or in liquid. And is there a difference or isn't there? Well, could be a big difference, could be a small difference, and we have to have some idea of which it is. Well, my colleague Patrick Carroll figured out a very nice way to do this. But before I say how he did it, let me just say something of the fact that this was the importance of the gas phase measurements were recognized a long time ago. There was a French chemist, Yale, the one who discovered that liquids could rotate the plane of polarization of light. He took turpentine, something you get from trees. Your parents or grandparents probably used turpentine as a paint thinner. It's a very common compound for a long time, cheap. And he measured the rotation in the liquid phase. And that was fine. He demonstrated that not only crystals, but also liquids can rotate the plane of polarization. And then he said, well, how about gas phase? Well, the problem with gas phase, we have a cell like this, full of liquid. Now, you can imagine how few molecules of gas would fit in a cell like this. So the number density is low. You don't get many molecules in the gas phase, so you need long path length. So he thought, well, where's the longest path length I can get in an enclosed space? You need a closed space because you had to shine light through this. You don't want daylight to come in and interfere. And it happened that churches at that time were constructed like this. So, as a cross. And at least one of them had a basement. And he borrowed the basement. This had a long axis. And he put together an apparatus that looked something like this. He had a tube, insulated tube, some kind of plates at the end, a place here for air to escape, and then down here he put a boiler, metal flask full of turpentine. And this is a big apparatus, this is a long distance. So this is a gigantic tube. And so you had to have a lot of turpentine, so he built a fire under this, probably charcoal fire, and he started boiling. Well, turpentine boils at 135 degrees centigrade. That's pretty high temperature. So he got this boiling away, and the turpentine was coming through here, and the air got displaced here. And at one point, when it was filled with turpentine vapors, he had a polarizer here, another polarizer here, and he found he had to rotate this one in order to get a null condition. And so he determined that turpentine vapor was optically active. It wasn't something that's just property of liquids, but they didn't know anything about structure at that time. And vaguest notes. They were still arguing whether there were such things as molecules. So, it was a big deal to tell that something in the gas phase would also rotate light. But unfortunately, just after he had shown this, this boiler burst. It had a lot of turpentine in it. And turpentine is very inflammable. So you can imagine what happened. Got a big fire in the basement of the church. I'm not sure how much of the church was damaged. I think the damage was quite considerable. So this experiment has never been repeated. So the question is, how can you simulate this without having this damn long tube? Now this is what Professor Vaccaro did. So I've got 5 minutes, I guess. I'll make this quick. Suppose you have a tube which you could put a compound and a couple of mirrors. And now you put a pulse of monochromatic light into here. Well, a little will leak through. And when it gets in, it'll bounce back and forth. And that's all very fine. And something will come out. And this is used for measuring absorption for compounds that are very weakly absorbing. Because you can have long path lengths, because you can have a lot of passages back and forth. The only catch is that a mirror reverses the rotation of a compound. So in the forward direction it rotates this way, in the back direction it rotates that way, and you get no effect. But his ingenious thing was to put in a couple of quarter wave plates. And the quarter wave plates, unfortunately, are quarter wave only for one wavelength. So for the wavelength, you use a laser, put in a pulse, and when it bounces between these two quarter wave plates, the rotation was reinforced, and by putting out a device which will separate the two components of the light, one that corresponds to the input and one at right angles, photomultipliers here, you could see the difference between having a compound in here and having it removed. And from that, you can calculate the rotation. And he gets effective lengths on the order of a kilometer. A kilometer is a hell of a lot better than this. So, by using this ingenious device, we can show that rotation can be measured in the gas phase. And it's one example. Here's alene, type of compound you may hear about later. These two groups are right angles to each other, so this is optically active. In the liquid phase, this had a rotation of 81 degrees. In the gas phase, it was 150 degrees. The largest change ever observed. We still don't understand it. We've had a couple of ideas, one of which we demonstrated was wrong, and the other one we're trying to figure out how to implement. So someday we may understand that. But at least it's worth doing in the gas phase because the numbers are different, and the gas phase value agrees with the calculation, whereas the liquid phase value, you say, God, the calculation must be awful. Okay, that's it. Thank you.
So you've heard from the expert on this subject. If there's any questions you'd like to ask him? This thing about doing this, about calculating things with the sum. So you have one electric. You have two states that you want the electron to go between, and you have how much the electric part does and how much the magnetic part does. But isn't it a problem often that when one of them's big, the other one's small?
In which case you don't get any rotation.
You don't get it. But you have a zillion of these to try.
That's right.
And in many cases, like if all you wanted to do was see whether the thing would absorb light, there's going to be just one of these that's going to have a big value of the M part. And that's going to do the trick, and you can ignore all the
That's
others.
right.
But if you have this, where you need the product of those two, and you don't know one of them's going to be big and the other's small, in almost all cases, and rarely are they both going to be big.
That's right.
So it's very difficult, isn't it, to predict which ones will actually are going to make the difference before you actually do the calculation.
Very hard to understand even after you do the calculation. So this is the rotation, and this is the number of states. We just keep summing up the values for the states. So you may go up like this. And finally it settles down. And typically it takes about 1,000 states before it settles down. So the first transitions usually have nothing to do with anything. Very unfortunate. So we don't understand much about optical activity. We've still got a lot to learn, and maybe some of you will figure out what's really going on.
So it's just a heck of a lot more complicated than almost anything you do.
Yeah.
Because anything that was simple, any simple relationship, people would have figured out a long time ago before they even had quantum mechanics. But this was just a complete mystery.
That's right.
And it's only going to have the really big computers that you can make accurate calculations of these things, and then sum up 1,000 terms or more in order to see what the thing is. So understanding it is going to be a real problem in really simple terms. Was there a question back there? So if you all understand this well now, maybe I should put it on the test on you. Right?
If he does, he'll shoot me.
Maybe wrong. Okay, this stuff. I think you should thank Dr.